Okay, let's solve today's LeetCode problem. We're given a 2x3 board, and on this board we have numbers from 1 to 5 and an empty space, which is represented by 0. We have to slide these numbers through the board. Basically, we take a number, for example 2, and the space, and we swap and we basically slide this 2 into the place of space, and basically you're swapping this 2, the empty space and 2, or you can swap this to adjacent 0 and 4. Basically means that you're swapping this space and 4 and swapping space and 5. And you need to find the minimum, the least number of moves required so that the state of the board is solved. The state of the board is solved when the first 3 is 1, 2, 3, and this one is a 4, and the next one is a 5, and the last one is a 0. So basically empty. This is when the board is solved. If this is not possible, if you cannot reach in any way the solved state, you'll return -1. Now let's see how we can approach this problem. Okay, we see the first example here. We have 1, 2, 3, 4, 5, and there you have an empty space. And for this test case, it is possible to reach the state where we have 1, 2, 3, the solved state, and 5, and here will be 0, basically empty. So the way we can do it is to swap this 5 into this empty space. Basically, we have now here 5. Now we have here 5. And this is going to be the empty space. So the state is 1, 2, 3, 4, 5, and 0. This is what we want. This is the solved version. Okay, how we can then think of solving this problem? We're given a board. The board is quite small. It's 2x3. So there are in total 6 numbers from 0 to 5. So the available states of board, all the possible cases, is 6 factorial. Basically, you have the permutation of this 6 number from 0 to 5. You just put them in this board. So this is about 702. So every time, so that means we can, if we decide to brute force or simulate this process, we can easily do that. Because 720 is not a big number. So we said that the search space is quite small. So this immediately hints at solving this problem, like approaching this problem from a brute force perspective. It's sort of like checking every possible case. When you see this empty space, you can see that there are 3 values that can slide into this empty space. 4 can go here. So in this case, when 4 goes here, we're going to have 4 here and an empty space here. And 5 also can go here. And we might have the empty space here. So if we have to generate a tree-like structure for this test case, let's look at this. 1, 2, 3, 4, I'll say 0 here, 5, right? For this 0 can be swapped with 2. So if we swap this with 2, that's what we get. We get a new board state. We have 1, 0, 3, 4, 2, 5. And 0 can be swapped with this 5. And if we do that, we get this board state. 1, 2, 3, 4, 5, 0. And 0 also can be swapped this with 4. And if we do that, this is what we get. We have 0, 4, and 5. One of this, if we keep doing it, if we can still do it on this board again. Like we have 1, 0, 3, 4, 2, 5. Imagine that you're given this board instead of this one. So we can keep doing it. Like we can go down this tree. Now if we do this one more time, we have 0, If we can slide this back to here, but we can slide this actually back to here, like 0 and 2, but this will give us this board, previous board, but we don't want that. We have seen this board, so we don't do this. We only swap. There are two cases when we swap 1 and 0. So this generates this board 0, 1, 3, 4, 2, 5. Or we swap 0 and 3, and this generates this board 1, 3, 0, 4, 2, 5. And we can keep doing it, but we don't have to, because we have already in the first level of this tree over here, we can see that we have the board solved here. This is the board's state that we're looking for. This is the target. The target is 1, 2, 3, 4, 5, 0. Once we see this board state, then we stop at that level. We've gone one level down to reach this state. So this is the least number of swaps, least number of slides, basically, that is required to reach the final state, because we can see this board state in the first level. Okay, this level-wise idea of swapping values, by the way, this is the third example. This idea by generating the tree, the idea of generating this tree, looks pretty logical. Now let's keep on this idea. We have 4, 1, 2, 5, 0, 3. Now for 0, we have this pair here that we can swap, or this pair and this pair. This generates 3 new board states. Now let's look at this board state one by one. So we have on this side, we have 4. If we do swap this way, then we would have 0, 2, 5, 1, and 3. The next state is this 5 and 0. So we have 1, 4, 2. The 0 swap with 5 and 3. And the last one is 4, 1, 2. We're swapping this one 5, 3, 0. Now we have 3 more new states, 3 board states. In each one of this represents a board state. For example, the first one is like this one. We have 4 here, this is empty, this is 2, 5, 1, and 3. This is this board. So in level 1, this is all the board states we can get. Basically, from the initial board states, in one move, this is where we can reach. This is where we end up. So basically, given any one of these boards, it only requires one swap, one move, to reach this state. Now, if we keep doing it, but as you can see, we have a target. We want to reach the solve state. It's 4, 5, 0. Among these boards in this level 1, we don't see 1, 2, 3, 4, 5, 0. So we have to keep doing it. So then we go over here. We do the same thing on this board. This board is generated by swapping 0 and 1. So basically, this is the board that we can get in one move. Now, from this board, let's see what board stage we can get in one move. So now we can swap 0 and 4. Let's do that. If we swap 0 and 4, this creates this board. We have 0, 4, 2, 5, 1, 3. And we can do that on this side as well. 0 and 2. We can swap that. We'll get 4, 2, 0, 5, 1, 3. And we can also do that, but this will make it 4, 1, 2, 5, 0, 3, which is this board back up here. So we don't want to do that. So we only have 2 new boards. Among these 2 new boards, you can again, we don't have 1, 2, 3, 4, 5, 0. Let's let's get, so these two boards on this level, level 2, if we have any one of these two boards, we need only 2 moves to get this pattern here, to get this board state. First, we would do only 1 move to get here, and then we would do only 1 move to get here. So that adds up to 2. So we need 2 moves to get to this state. So that is the shortest we can do. Given this state, and if our target, for example, was this, and we're given this one, then we could say, okay, it requires only 2 moves. So, but our target is this one. So we have to see this one somewhere down here. Now we keep doing it. We have 4, 1, 2, 0, 5, 3 in the first level. So from this we can generate 2 more boards. I guess 1 more board, because if we swap this 5, 0, and 5, this will give us the same state, but we can only swap 0 and 4 to get a new state. So we'll have 0, 1, 2, 4, 5, 3. Now let's just write all the board states. Okay, now I've fully drawn the tree. Yes, we can go down again, like there are more levels, but that is enough to show the point. Now you can see from the first initial point, we reach this 3 board states. Basically, these boards are telling us that, okay, we require only 1 move to get back here. So, but none of these boards are solved ones. So this is the target. So in level 1, we could not find 1, 2, 3, 4, 5, 0. So for this reason, we'll look for this target in the level 2. In the level 2, we have 4 more new boards. And these boards, if we do 2 moves, we'll get back to the initial state. Again, we do not have our target in this level as well. And then from these boards, we generate a new board. So this board will be on level 3. On level 3, we have again this 4 boards. And again, none of these boards is the target one. But we can make this as, so we can make this equal to the initial board state by making 3 swaps. We'll do 1 swap, and then another, and then another. So this is basically what happens to the board states on level 3. Now from the board states on level 3, we get to the board state on level 4. On level 4, we have these trees, these boards, and out of these boards, you cannot again see this target solved state. So we move 1 level down again. So we move 1 level down, and these are all of the board states in level 5. But if you notice that we've got our answer here, we have 1, 2, 3, 4, 5, 0. So this one here is the solved one, the solved state. This is the target. This means that we're at level 5. So we just have to go 5 up the tree to reach the initial state. And this is also the same for the initial state, from the initial state to the target. So we have to go down 5 levels to reach the initial state. So that is the shortest we can do on this tree. So basically, this says that 1, 2, 3, let's just swap some value to get here, this 2. 1, 2, 3. In particular, we swap this 3 and 4 in the initial, the solved state. But basically, we're going back up from the solved state. So we just do 1, 2, 3, and to get this, and from this way, we do 1 more move to get this, and then 1 more move, and 1 more move, and 1 more move here. So if you want to know concretely what we're doing here, like what states, what we're shifting, from this we have to get this one. It's a big on on this path here. We have to go down on this path. So we have 0 here, 5 here. So then we swap this 2, right? We swap this 2 and get this board. So in our initial state, 5 just slides into this empty space, and this becomes an empty space. So that is the first thing we do. And then what we do is to swap this 4 down, slide this 4 down, and basically now this was empty, 5 here, and 4 goes down to this spot, and this one is empty. So we then after that, when we have this board state, what we do is to swap this 1 into this empty space, so 0 and 1, and then we get this board state, and from this board state we swap 2 and 0 to get this board state, and after that we get this to this board state. Then what we do is to swap this 3 and 0 to get our solved state, which is our target. So you might already notice what we're doing. We're generating all the moves, which we said that there are 720, and by the way, not all of them are valid boards. They're not solved. Not all of them are solved. So there might be, for example, in the second example of the problem description, there was the one board that cannot be solved. So that is not possible. Basically, it means that if you take that board and keep generating this tree, you will never reach. You will exhaust all the possible board states, and out of all this board state, you will never see the target one. So that's because that is not possible. That is unsolvable. But so basically, we have at most 720. That is the maximum number of this boards on this tree. That basically these are nodes like on a tree. So that is a small tree actually. So what we're doing here is the breadth first search. We're processing the board state level by level. We're saying, okay, from this initial state of the board, what are the states of the boards that I can reach in one step, in one move, in one swap? So these 3 are the ones that we can reach in one move. So that is in one move. And the same goes for these levels. For any of these board states on level 1, what are the board states that we can reach in one move, which will be the board state that we can reach in 2 moves from the initial board state. So basically, this board state, from this board states, these down here, these board states are the one that we can reach in one move. So from this is one move, and this is one move. This is 2 moves to reach the initial state. And if somewhere on the board, just like we did here on this tree, if we see our target one, and then we stop, and the answer is the level, the number of levels we have gone down this tree. So we have gone down 5. So we go down 5 levels, and we reach our target here. So the answer is 5. In 5, at least 5 moves is enough to reach this solved state. So that is the approach that you can take. You have the board, and for each board state, generate the next board state. So basically, these are nodes of the tree, and then from this tree, what are the nodes that you can go? These are other nodes. So process this as the breadth first search, level by level. So that is one approach. But actually, I didn't use this one. I go backwards. So this is most of the time that I come from the answer, the state, the goal of the problem to the actually unknown. So I knew that what is known, I have to find the state. The state is always known. This 1, 2, 3, 4, 5. That is the sure thing that I know about the problem. That means the given state, I have to reach this state in minimum number of operations. If this is not possible, then we just report that it is not possible. But so instead of doing this one, instead of generating down here, I did something different. Now let me show you how I did that. The core idea of my solution is the same as the previous one. We'll do again the level by level, level-wise traversal of the tree. But instead of going from the given state of the board, which is for example this one, we will go from the known, what we know. We know the state, the final state. We'll go from whatever we have at hand. We'll go from this one, the final state, to other states. Basically, that means, now think about this one. 1, 2, 3, 4, 5 is the solved state, right? Then what could be the other states one move before this solved one? It could be either this swap this 3 and 0. It could be the 1, 0, 5, 4, 5, 3 here. Or it could be 1, 2, 3, 4, 0, and 5. You see, these two boards only requires one move, so that is the same thing. But we're going from this solved state to other state. That only requires one move back to reach the solved state. And we keep doing it the same thing for this board as well. For this case, and we'll have another board here, another board here, another board here, another board here. For each of these boards, it only takes 2 moves to reach the initial state. And from this, on the second level, on the level 2, we again generate the next boards. Let's say there are some boards, and we keep doing it. And this on the level 3, for given any one of these boards on level 3, it means that we need 3 moves to reach, at least 3 moves to reach the solved state. So basically, what I did in this solution is to generate this tree starting from the solved state and keep the answers for every board that is possible to generate in an array or whatever in a map. Then when the problem asked, okay, what is the minimum number of steps to reach the solved state from this initial state, I'll look up the value because I've already pre-computed it. And if the value exists, then I'll report the answer. If it doesn't, because when you start generating from this one, you will never ever generate in an invalid, a board basically that is not solvable. Because from this solved state, when you generate the next board, you're only considering the possible cases. So if out of 2000, I believe the great majority of this board states are unsolvable. But when you do that, you actually not considering all these boards. Maybe there are 200 boards that are not valid. So you actually, when you generate this tree, you're actually considering 520 boards on your tree. That is much less. And for each of these possible cases, for each of this board states down this tree, you store the answers. For example, for this board, and this board, the answer would be 1. And if it happens that in one of test cases it asks for this board, you'll just say, okay, I have this, I have already computed it, so the answer is 1. If it asks for this one, you'll say, okay, for every you know that every board on this level needs 2 moves. So I'll say, okay, the answer is 2. So basically, you store all of these boards and the answers for each board. So that is much more efficient because we only do this once. We just do this whole thing once. We start from the initial state, the final state, the target. We generate all possible boards level-wise. We're basically starting from this. We're doing a breadth-first search, and we're generating something like I'm pretty much sure it's less than 720, something like around this or even less than that on your tree. and you store for all of these boards the answers for this board states. And then it doesn't really matter how many test cases they ask. They can ask like 10,000. They can ask like 20,000 test cases. It's just going to be a lookup. You just say, okay, you're telling me what is the least number of moves, least number of swaps it requires to reach the solve state. It is just 1, 2, 3. So 1, 2, 3. So I have the answer. So I have stored it in somewhere. So then you just return. So the only thing you do is to pre-compute one time, only once, and then answer. Then you just do a lookup. Now let's see the code for this one. Actually, before doing the code, let's generate the board states for this one and for this approach, and let's see if we can reach this given board state. Okay, we have generated some levels of this tree, and our current pattern is 4, 1, 2, 5, 0, 3. That is the one that we need. 4, 1, 2, 5, 0, 3. So you can see if we go down, we'll find it at level 5. So everything on this level, if we're given even this board, we can say, okay, the answer is 5. If we're given this board, we can say, okay, the answer is 4, because you have stored the answer for this board. If we're given this board, you'll say, okay, the answer is 2. We're given 4, 1, 2, 5, 0, 3. It's on level 5. We'll say 4, 1, 2, 5, 3. Okay, the answer is 5. So there you go. So if you're given this board, so then the answer is going to be 4. If this board, then the answer is going to be 3. So basically, we generate all possible boards, and for every board, of this tree, we just store the answer, basically the level number of the board where the board appears. This board is in level 4, so the answer is 4 for this one. If we're given this one, we can say, okay, it only needs one move to reach the solve state. So that is basically how we do it. Now, instead of starting from the initial from this board and go down the tree to find the solved one, we actually first just once. So if we do this approach, then every time you'll given a board state, and there could be like thousands of board states. So I know that there's 720, but you'll given like maybe 10,000 inputs. Each of them have a state, so have a board state. So starting from board state, and every time you're given this input, you have to go down the tree to find this one. But you can only it's enough to do this approach once, only generate this tree once, and have the answer for all of these boards. And once you ask some board, you just say the answer. If the board is not valid, you don't have this board. You have not generated the board while you're building this tree, so you don't have the answer for this one. So you just return -1 as the problem requires. So this approach is much more faster. In fact, every time you run this, it will give 0 ms or 100% beat. So this way you can get pretty fast. Now let's see the code. Okay, for the code we have a little bit long one. You don't have to know what's going on here. This is row size and column size. I have represented the board with a structure. You don't have to do that, but for me it was much more clear this way. I have the board, and the internal what's happening internally is not of importance. So we have the operators, some hash function. So I use the hash function. I see some people just basically converted this board, because we have to store the answers for board in a map. We probably do this in a map, but the boards are just discrete. How do we store this? Like, we have to have a unique ID, so we have to have a unique value to identify every board state. For this reason, some people like convert a board state like this one into a 1D array, or basically in a string. So if we're given 1, 2, 3 and 4, 5, 0, they just have a string of 1, 2, 3, 450. And for strings, the hashing them is easy. You don't have to have any hash function. Just use the standard library stuff. You can use map or unordered map. It will work. But I've actually done a little more. I guess I don't have to do that, but it's fine. So I have a hash function. This is sort of a rolling hash. So it doesn't really matter as long as it gives you a unique value for every board, which this one does. So basically this is the board. This is the representation of board and nothing more. Just think of it like a black box. And then we go down. Here is the main deal. That's pre-compute. We will call this only once. Inside this minimum number of moves, this is basically the answer. This is where we store the answer for the board states in every level. We have the ID. Basically, this is the ID of the board state, a unique value for every board, and the answer, the minimum number of moves for that board. First of all, we have the directions. This is a convenient way of processing the four direction, so up, down, left, and right. And then the grid. The grid is the first the sol state, and then we pass this to a board. So I basically create a board. Then this is the usual setup of breadth for search. We have a queue. Into this queue, we push our the top of the tree. It was the first node, which was this initial state. So this sol state. And for the first one, it's just 0. So we don't have to do anything to reach the sol state if we're at the sol state. And then as long as we have some values in the queue, we get the value in front of the queue. We pop it off the queue, and then we process all four directions. First of all, we need the position of 0 because that 0 represents the slide, the empty space where we basically slide the outer value. This is a swap. So basically you're swapping the place of the 0 and another value. So we find the position of 0 here, and then we process the directions. This is some direction. It's either left or right, so we're processing all of the four directions. If this is out of the board, so basically it's not valid. Otherwise, we'll swap this to 0 and that value, whatever it is in that spot. So then we get the hash value. We have then basically this is a new board, and for this new board we get a hash value, a unique identifier. And if we have already generated this board, we just swap. Remember, we have to undo the process of the swapping. We put this back to the previous state, the board. We don't want to ruin the board because we will need this board, the level and the board that is in the current level, because we use this board to generate other boards. So basically we swap it back and continue because we don't have to do anything. We have already generated this board state and have the answer for that. Otherwise, we push this new board into the queue to process it later, and then we swap the board again back to its own initial state. The answer for the generated state, remember this is the hash value of this new board state, is equal to the previous board. Previous board, basically the current board, plus the 1. 1 is just we go just down one level. And what I mean, like current, it is the previous node. Let's say the first node, and then we generate, and this goes down one level. That plus 1 is that one, and whatever the answer for the previous, the board state that is above this new board state. And then inside this constructor, basically they use this constructor. They create this solution object. When they call the solution object, we also call the precompute. The LeetCode only creates one object of this solution. So that just means the precompute is called just once. So we call this once we do this process here, whatever it is, this is just the usual breadth-first search, just once. And after that, we'll just, when they call this function, they give a board state, and then we created a board and we get its hash value, and we said, okay, do we have this in our among our board states? If that is there, so then we're just going to return the answer. Otherwise, we're going to return the -1. That was a nice problem, actually, that requires you to find that you have to use breadth-first search. There was actually another problem. It's called, I believe it was 752 open the lock. It was also some sort of like something like this, the breadth-first search. In most of the problems where you're given a game or something like a lock or a board like this, and you have to reach another target state, and if the board or the representation of the input is small, just like this, in this case it's 2 by 3 grid, then check, so see if you can generate all the possible cases. And if the problem asks what is the minimum number of moves to reach here, what is the, so usually you see like problems like solving a maze, solving a puzzle, solving a board game, so given this like board, and you have to reach another state, you do some changes on the board and you get new states, and from those you get new states. You basically, when there is an ideal level-wise processing, and if it asks for the minimum number of moves, and you can create, and if you can create this state between the current input and the next, what you can generate from this input, then there is a link that basically go from this state to this state. Then there is something like a graph or a tree on which you can use breadth-first search to find the minimum number of moves to reach a specific state. This was a nice problem. Yeah. See you in the next videos.